This is tutorial 6, question 2. And the question goes as follows. A Second World War airplane has the following specifications. One wing is 4.5 meters long. The area of one wing is 8 square meters. The air density is given. Angle of attack is 10 degrees. And the fuselage drag coefficient is 0.9. The rate of climb 17 meters per second. Horizontal speed is 280 kilometers per hour. The wing coefficient of lift is 1, and the wing coefficient of drag is 0.016. Frontal area of the fuselage 0.81 square meters. So firstly, calculate the aspect ratio of one wing. I have pasted at the top of the question the diagram showing all the forces and their components on the aerofoil section for reference. Alright, so the aspect ratio is equal length squared over area. So that is 4.5 squared over 8, or 2.5312. So secondly, we need to calculate magnitude and direction of the relative incoming air velocity relative to horizontal velocity of aircraft. So that is actually CRM. That is the relative velocity. If we look at our diagram, we can see CRM is the label shows local relative wind. So that is the relative air velocity to the wing. So CRM equals the square root of 17 squared plus 77.778 squared. And where do we get that? So if we draw a diagram, and that is CRM, this is BM, beta mean, 280 divided by 3,6 will give us 77,778 meters per second. That's our horizontal velocity of the aircraft relative to the ground. We also know the climb rate of 17 meters per second. So therefore we can calculate CRM using Pythagoras. And that will give us 79.61 meters per second. We can also calculate the angle beta, BM, that's arctan of 17 divided by 77.778. gives us 12,329 degrees to the horizontal. Alright, so that's what we needed to calculate. The third question is the vertical lift force produced by both wings. So if we look at our diagram again, we can see all the vertical forces involved here. We've got the vertical component of the lift force FL, which is FL cos beta, and we've got the vertical lift force of the drag, which is FD sine beta. So those are in opposite directions, so we would subtract them. The lift minus the vertical component of the drag force. So F vertical is rho A 0m squared over 2. We've got CL cos beta minus CD sine beta. Those components being in opposite directions. 1,18, 8 times 2, because that is 2 wings, and 79,61 squared. We divide it all by 2, and then multiply that by cos of 12,329 degrees minus 0.016 sine 12,329 degrees. Coefficient of lift is 1. Alright, so that gives us a vertical force component of 5,8,244,2 newtons. Alright, so now we need to calculate the horizontal drag force produced by both wings. So if we look again at the diagram, the horizontal forces are the blue ones. So we have FL sine beta m and FD cos beta m, both of them in the same direction, so we will add those forces together to get the total horizontal forces. So that's rho A, which is the plan view, and CRM squared over 2, and here we got CL sine BM plus CD cos BM. Substituting 1,18 times 16 times 79,61 squared over 2 and multiplied by sine of 12,329 degrees plus 0,016 cos 12,329 degrees. Horizontal forces total 13,710 newtons. Number 5, total thrust required from the propeller. Alright, so the thrust is equal to the drag force of the wing plus the drag force of the fuselage. Half rho CRM squared CG plus Alright, let's substitute. Area of the wing is 16 square meters times 0.016 plus 0.81 times 0.9. So the thrust required for the propeller would then be 3683.18 newtons.